Hello. Hello, everybody. Hi. This is lecture six. This is lecture six. And lecture six is cool. Uh, there's so much about electricity that I would love to tell you all to cover throughout this course. But as you know, this is a physics course that is not just about electricity. It's about a lot of aspects of physics that'll be useful for you going forward in your major like biology or in your career like possible future uh, physician's position or other kind of biologically based healthcare related type work. So it's really important that we say what needs to be said and then move on. And I wish we could go on more because we go into great detail and have a great time with it. But that's okay. There's still a huge amount of great fun to talk about. And today we're going to go forward on the electrostatics that we were talking about and think about what happens when charges move. Remember the first unifying question about lightning, right? What is lightning? Now the second question becomes like, what's the deal with lightning? Can we put lightning in a bottle, so to speak? Can we understand how to control it, how to move it around so that it can do the things we want, right? Think about it. Lightning is incredibly powerful. We now understand that the amount of power in electricity is tremendous, right? The amount of power you can get, the amount of force that you can generate with just a small amount of electrons, a little bit of electricity, is equal to the amount of energy you would produce by putting a huge amount of other stuff together. Now, remember in your previous physics classes, like physics 116, so forth, you talk about dropping bricks or boulders or rolling cars and things like that, big things. Well, we can do big things with little tiny electrical stuff if only we could understand how it works. So here is some basics that we're going to talk about here in lecture 6 about how that stuff works. It has to do with this thing called voltage. All right, we're going to get to that. We're going to move in that direction today in our conversation. First, let me share my screen with you and show you where I want you to look for these cool things. Additional information. Remember, not just my lectures, but all these other things that will give you the opportunity to understand or to help you pick up all these concepts. The first one, both of these, by the way, I've mentioned in the study guides before, but I just want to be sure that you understand what we're talking about in person. So this physics in motion program put out by the Georgia Public Broadcasting folks is really an excellent series with lots of high quality videos on what to do. In fact, if you were wanting to review some of the stuff that you learned in your previous physics class, physics 1 class or something like that, then here's some great stuff that's involved with that. We have segments about what is physics, significant notations, vectors and scalars. We're talking about doing the static electricity charges and pushing back and forth on those with different kinds of forces and vectors. This is actually very helpful if you want to review this stuff here. We'd mentioned that before as well. We talked about motion, right? About speeds, forces, which will happen throughout your whole life. The whole concept of forces is such an important part, not just in physics, but in life, right? Then momentum and energy, if you remember that, how you wind up telling the difference between kinetic energy and potential energy and the concept of what work is as opposed to what energy is, how they're basically the same thing, but there's a little bit of subtle difference that you can think about. And then electricity and magnetism. Here is where we are so far in physics 2, right? So this intro to electricity, static electricity, Coulomb's law, this is the stuff that we've been talking about for the first few lectures, up through about lecture 5, and about all those things. Now here, we're going to talk today about this electrical potential energy and electric potential, and then we're going to start talking about all the rest of this stuff a little bit later, right? Resistors, capacitance, series circuits, electrical power. It's great stuff. This particular segment D will be especially useful in your understanding of what the class. In fact, the study guide requires you to watch this because there is a demonstration or an example that's done about electrical potential energy and electrical potential in general, which again, electrical potential is a word that you've heard of before in a different thing, and that's voltage. Okay, I know that. Why do we use these complicated names, electrical potential, as opposed to voltage? Well, if you use the term electrical potential, you get a better sense physically of what it's actually doing. So calling it voltage is just something that we're used to, But electrical potential energy, these kinds of things, puts it in the context of overall physics and thought process. Okay, so it's not potentially designed to confuse you, but is designed to give you an understanding of where we're talking about in terms of energy, in terms of potential, in terms of power, those kinds of things that actually matter. It's just that it's in the context of electricity. Does that make sense? So make sure to go to that Georgia Public Broadcasting, the Physics in Motion series of videos. That'll be extremely useful to you. The other thing, which we've talked about already, and we'll talk about some more, is the textbook, right? The OpenStax astronomy, OpenStax physics textbook. You can tell that I also teach astronomy. The OpenStax physics textbook, and we've talked about this a little bit before, but I want to talk about it in greater detail now. All right, let me explain what this class is about. Now, this physics thing, right? This is just a little section here about introduction to electric potential and electric energy. But let me remind you, if you haven't been there recently, right, this whole book is a 1,568 page book, which you can print out and you can actually like buy in a hard copy if you prefer, or if you just want to look in the PDF, you can print it out, have a local copy. There's nothing wrong with doing that. In fact, I might even recommend it for some of you who might wish to have just something on your local hard drive just to have it, right? See, here's the example of the book. And so notice all these different pages, and notice it's electric field inside a conductor, electrostatic equilibrium, these kinds of things that we started talking about in the previous lecture, right? The electric potential, electric field, those kinds of things. It's put out very nicely in this demonstration expression. And so we're talking about 18.6, 18.7, that sort of thing. So you want to know how to do those kinds of problems and questions. Here is your opportunity to play with them. All right. And I want to remind you, we've talked already about 18, right? Chapter 18. You've done some questions about chapter 18 already. So what we want to do now is move to chapter 19, right? Which is this electro potential type stuff that we're talking about here. Okay, electric potential. And if you go on the electronics section, section of this textbook that starts around chapter 18, which we talked about in great detail for the previous lecture, and now chapter 19, electric potential and the electric field. So you want to read chapter 19, the section Introduction, Electric Potential, Electric Energy, and then 19.1 and 19.2 and 19.3, right? These are the areas that we'll be talking about specifically in this particular lecture, all right? So be ready for that. I'm going to be sharing the screen quite a bit so you can get a sense of the kinds of things that are going to be talked about in this conversation, all right? Here's the basic point for these electric potential type stuff, okay? We talked already using this. Imagine you have a charge. If you have a charge, then that charge produces an electric field, right? And I remember I brought a little extra cue. If I bring the charge in close, then it produces a force between the two of them, because that's how electric potential field works, right? Now imagine if I had a situation, we'll just idealize it, okay? Imagine if I had a, say, plate, metal plate here, okay? A metal plate. And so I'll draw a little extra plate like that. And on this plate, I put positive charges, a whole bunch of positive charges, all right? Say a lot of protons or something, put them all up there on one side, right? What's going to happen? Remember, each one of these charges, right, produces an electric field. Combined together, they all produce an electric field, right? And if you do the things with the equipotential lines and where they push and everything like that, right, artistically, what basically happens is they all create this sort of wall of force, a wall of electric potential. The electric field kind of turns into this kind of downward, outward thing. Because see, in this direction, right, you have all of every one of these charges all along this plate, basically pushing, creating this force. So together, they form this sort of field that pushes downward, right? So any electric charge that's put in this field, right, this big plate field, winds up feeling a force. That's kind of all kind of in one direction. Does that make sense? So instead of just having this single circular thing that pops out like this, right? Now we have like a whole line of charge, a wall of charge in a sense of I don't want to use the word charge so much, but the electric potential field is this big, long, big thing like this. Okay, so that's kind of cool. So what happens now? What happens if I take a second plate? I put a plate down here, right? Like that. And this time, instead of putting a lot of positive charge, I have a lot of negative charges. What's going to happen now? Well, remember this negative charge, right? It's got its own force. It like has an opposite direction as the positive charge. So maybe it's like pulling toward it. So you got this force coming down this way. And so really, if you have this situation, you're having the charges pulling down this way, right? Or might have charges going up the other way, depending on how you want to think about it, whether it's electrons moving, right? Or protons moving or things like that. So the electrons moving down in this direction, shall we say, is making this area more positive. This area is more negative. And let's say there's a continuous situation going on here. You always have all this positive charge here. You always have the negative charge here. There's basically a field of force, right? If I want to take a charge, say I have an electron, negative charge, and I want to move it in this direction, or if I have a proton, I want to move it in this direction. Notice that this is going to be repelling it because it's positive proton. And then you have an electron here, negative. It's pulling it down. So I actually have to exert a certain amount of energy to move the charge from down here to up here, right? By the same token, there's a natural tendency to push charge from here down here. Push, 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 right? So there's a difference in the electric potential. That push, all right, that push acts like a way where you're moving energy from one side to the next. In other words, if I'm going to take charge and move it from charge from here down to here, how much energy do I bring along with me, right? So if I have a certain amount of charge, remember we're measuring charge in terms of like per electron volt, or excuse me, per elementary charge, like per the charge of electron, right? How much per energy per electron is being transferred from one side to the other if I just let it go, right? What is that difference? The potential difference which allows me to basically move energy from one side to the next. That's through the force field, right? That's bottom line. If you take charge from one side to another, and if you move that charge, you're not just moving charge, you're moving energy. And depending on how strongly different, right, the two are, you can wind up moving large amounts of energy for a small amount of charge, or small amounts of energy for a large amount of charge. Okay, so here's what we do. You know from your Physics 1 class that the unit of energy is a joule, right? It's a joule. 1 joule equals a kilogram meter squared per second squared, like this, right? That's the amount of energy that comes out. And so what I want to know is if I'm moving electric charge, okay, between these two plates, between these two differently charged plates, and there's a difference, right? They're different. If I try to move a certain amount of charge in this direction, for every bit of charge, every unit of charge I move, how many joules do I get? How many joules of energy is delivered when that amount of charge is delivered? Okay, and remember that we had how much charge, right? A coulomb, joules, right? That's energy. And then meanwhile, 1 coulomb, this is from the previous lecture, right? A coulomb is 6.25 times 10 to the 18 electrons, right? Elementary charges, shall we say. That's a certain unit of electric charge, right? So if I want to know how many joules I wind up moving for every coulomb of charge I move, right? Then that unit you might imagine, is a joule per coulomb. Yes? Okay. So 1 joule per coulomb. And I'll write it, joule per coulomb, J per C, like that. Okay. And that is an electrical potential difference, right? And we call that 1 volt. That's a joule per coulomb. Oh, so when you talk about high voltage wires, remember that? And now you understand what well, maybe you all understood already, but this is how I understand what volt is. It's like, oh yeah, well, this is 110 volts, right? That runs through our electrical systems or something like that. What does that voltage actually mean? Well, it means that if I am drawing electricity out of a 110 volt socket or something like that, okay, so for every coulomb of energy, for every coulomb of charge that comes out of there, all right, we get 110 joules of energy. Is that a lot? Well, kind of, yeah. This is a half a full water bottle, but if I take this water bottle and I fill it all the way up, right, that's about half a kilogram. And so the gravitational acceleration of Earth at its surface, where we're around here, is about 10 meters per second squared. So if I take this half a kilogram, right, and I drop it 1 meter, so I got to take it way up high like this, and I let it hit my hand, it'll hit my hand, and it'll have the energy when it hits my hand, the kinetic energy of 5 joules. Okay, so that hit my hand, that was just 5 joules. So 110, that's 110 divided by 5 is 22. Imagine taking 22 full bottles of water, holding it up to 3 feet high, and then dropping it on my hand all at once, right? Boom, 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 boom. That's kind of a lot. That's a fair amount of energy, right? 110 joules. So every coulomb of charge that comes in that direction through coming at 110 volts means that I would receive 110 joules per coulomb. See? So that's what voltage is. And so when we want to figure out how much energy gets delivered, here's where the difference comes in. The amount of charge we were talking earlier, right? Like there's a defibrillator or something like that, gives you a certain amount of charge, but also how much energy does it deliver? That's where your voltage comes in, right? A high voltage power line or something like that, it's got like 10,000 volts, sometimes maybe even up to 100,000 volts, depending on how powerful the lines are, right? That is a lot of joules per coulomb. If you're transferring a certain amount of power through, I mean, that's a lot. So that's why you don't want to touch high voltage stuff, right? But remember, there's also another aspect. If it's joules per coulomb, right, then if you don't deliver a lot of coulombs, even if you have a lot of voltage, it comes through at a very high rate, but it might not necessarily like produce a lot of energy, right? Let's think about this for a second. I'll take an example. I've got a thing. You guys, by the way, know like how many volts your cell phone does? I'll get back to that in a minute. Okay, you should take a look on your cell phones and your small devices and see how many volts that it delivers at any given time, right? But you have a certain amount of charge. Okay, say I have something that's delivering something at a very powerful, say 10,000 volts or something like that. That feels like a lot, doesn't it? 10,000 volts. And because I use volts, I really mean 10,000 joules per coulomb, right? Like that. A device delivers that much. 10,000 joules per coulomb. But let's say it only delivers that amount of coulombs, right? How fast does it go? So you have to know also how many coulombs get in at any given time, right? So the amount of coulombs that come in any given amount of time, that's a different measure. So that's a different thing. Voltage, right, is different from this other thing which is how much charge comes in per certain amount of time. So that's a rate of how many coulombs will show up, say, in a period of time. Okay, let's say 0.0002 coulombs per second. Right, the C here is capital, right? Coulombs per second. So it's delivering a small amount of coulombs per second, but it's delivering a lot of joules per coulomb. Okay, what is this coulombs per second thing? Okay. You see it on your chargers, on your cell phone batteries, on those things all the time. That's called an amp. Okay, an amp, named after this guy Ampere, right? Amp, and that's, I'll put ampere, and there's some accents in here somewhere. You know that 1 amp, okay, equals 1 coulomb per second, like that. So you heard about like voltage, right? You also heard amps. They're not the same thing. They're actually quite substantially different than the coulombs, amps, but it's coulombs per second. So you have joules per coulomb and you have coulombs per second. So let's say this delivers at a rate of 0.002, something like that, coulombs per second. If I deliver it for a short period of time, right, then I'll get less energy. If I deliver it for a long period of time, I'll get more energy. So let's say I've got a device that delivers 10,000 volts at a rate of 0.0002 coulombs per second. Let's say I take this device and, I don't know, poke something for 1 second. Okay, what'll happen? How much energy gets transferred? All right, let's find out. If this device pokes a person, oh no, that's not a person, pokes a thing. Okay, it could be a person, but let's not, you know, jab people with electrical stuff. Pokes a thing for 1 second. Right? If it pokes a thing for 1 second, then it delivers, you got to multiply this, right? It delivers a certain number of joules. All right, let me write that down. The number of joules it delivers would be, right, 10,000 joules per coulomb times 0.002 coulombs per second times 1 second. And if you do the math, that comes out to be 20 joules. See, 20 joules. Make sense? 10,000 joules per coulomb times 0.0002 coulombs per second is times 1 second. You wind up with a certain number of joules. So that's how much this particular device might deliver to you. 20 joules feels like, you know, it's a fair amount. Think about it. How much? Remember, I took this, and if I drop this from 5 feet, from 1 meter, excuse me, I get 5 joules, right? So if I drop this from 4 meters, if I dropped a full water bottle from 4 meters, or if I drop 4 water bottles from 1 meter, I'd get 20 joules. I mean, that's a lot, right? I mean, think about getting hit by a water bottle that's dropped from a height of, like, say, a 2nd-story window. That doesn't tickle. That's a fair bit of energy, right? But in this instance, instead of having to drop your water bottle from the 2nd floor to hit something to deliver that much energy, instead, you just have this device, right, that's got 10,000 volts, and you can deliver that amount of energy in 1 second, just with that much. Turns out that things like defibrillators, cattle prods, tasers, right? That's the kind of thing that you deliver that kind of energy to. You put a lot of voltage into something, but for a short period of time, you'll deliver a little bit of current. Then you wind up delivering a fair bit of energy, right? you got to be careful about those things, of course. So if you want to deliver energy, you can deliver it more slowly. So if you looked on your cell phone, if you looked on your cell phone battery yet, look on it real quick, take a look, see at your cell phone how much voltage your cell phone uses. My guess is it's like around 5. Go take a look and find out. Oh, and have you been filling out your study guide? Make sure you're doing that while you're listening to this lecture too, right? And all those other things. So it turns out that your cell phone, right, it only needs to deliver energy at a slow rate compared to, say, your wall, right? Your wall charger, if it delivers 110 volts, if your cell phone only delivers 5 volts, then at any given time, the total amount of power, the electric, the potential, right, is much smaller. So you're delivering fewer joules per coulomb of charge. You don't need to deliver a lot of energy to your cell phone, right? You don't have to like smash it with a drop. If you dropped a brick from height and it hit the ground and it hit your cell phone, in fact, your cell phone would not be happy. But all those cool electronics inside your phone, right, inside this computer, inside all kinds of these electronics, there's a really subtle way of delivering energy in very fancy, sophisticated ways that allow you to use that energy and harness it so that you can talk to people, or you can text people, or you can surf the web and things like that, right? So it's really, really cool how this energy, thanks to voltage, right, and current, allows you to deliver these things together. And then the last thing I want to mention now, right, because then, again, so like I said, we got to move on to other cool physics stuff, because after this, we're going to talk about one last thing in the next lecture. Not this last thing we're going to talk about in this lecture. See the joules per coulomb, and then you have the coulomb per second, right? So if you add, what happens when you multiply these by 1 second, then you get a joule. That means that every second, you're getting 20 joules. So joules per second. If I multiplied this joules per coulomb with coulombs per second, I get joules per second. Think back to your physics 1 days. What is a joule per second? I'll say it again. What is a joule per second? I know it's a bad joke, but it's true. A watt, right, is a joule per second. So electric power, right, is just like other kinds of power that you're delivering in terms of joules per second. But in this case, it has to do with voltage and current. So if you take your voltage and you multiply it by your current, you end up getting power. Isn't that cool? That's really a fascinating thing. It's worth its own back of the envelope. Power, okay, P, power, is the current times the voltage. Like that, okay? Now, historically, don't ask me why, but this is what happens, okay? Power is capital P in electric stuff. Current is often expressed with a capital letter I, meaning intensity, okay? Okay, that's fine. The intensity of your, of the electric flow, right? How many coulombs per second? That's intense, man. If it's highly, many, many coulombs per second. Okay, I can get that. That's I, okay? Now voltage, of course, is V, right? So you can call it P equals IV, something you can remember. It's easy to do. But remember how we're talking about voltage is really this thing about electrical potential, right? We talk about electrical potential. And so because we want to keep the letter V, I don't know, I don't mind using the letter V, but sometimes people would prefer to not use the letter V for that. They will prefer to use the letter E, right, for electric potential, just to not use V for voltage. So this expression is pi, not 3.1415926 pi, but more like apple or cherry or rhubarb or pecan pi. Power, the power delivered by an electric current or an electric thing is the current in coulombs per second, for example, times voltage in example terms of joules per coulomb. Depending on the units you use, pi is always true. P equals IE. Or, I'll just write the other kind because that's kind of fun to remember. Also, it's the same thing, but I just prefer the other way. I just take this and turn it into a V, right? And then reverse it. And so I call it V times I equals P. So this is the very important electrical power equation, okay? VIP or PIE. These are just the ways that I remember it. But it turns out to be very useful, right? And seems silly, seems simple in some ways, right? But on the other hand, there's some complication understanding it. Even in the way that I'm explaining it right now, I apologize if in fact it seems confusing. Like, what is this joules per coulomb, the different electrical potential difference, electrical energy? It feels, complicated, but actually it's pretty straightforward and simple. But take some time, wrap your head around this. The concept is what matters, okay? Because this concept happens throughout your whole life. And in your body, if you're going to become a neurosurgeon or something like that, or doing neurological stuff, you'll find that basically we talk about volts all the time. Why do the brain cells, why do the neurons in your brain or along your spinal cord and all that, how does it transfer information? Turns out it has to do with voltage, right? We're not talking volts or even thousands of volts or anything like that. We're talking millivolts. All right, tenths of volts, hundredths of volts, thousandths of volts. But that's what's happening in your brain. Things are firing, your neurons. It's electric potential. And the way that our body uses our biological systems to change the electrical potentials from one side to the next, moving from one plate to another, from one piece to another, that is what causes our entire nervous system to function. It's really cool. So it's worth learning. All right, think about it. All the cool calculations about electric circuits, those are cool. But what really matters to you, maybe, right, is not so much as you can calculate like circuits and so forth, but the use of the cell phones, right? The use of electricity in our daily lives runs almost every device that we use, right? And in our own bodies. That electric potential, knowing how that flows, knowing what moves back and forth, that is the power of understanding electricity. Okay, so I hope you've filled out your study guides and so forth. Thank you so much for your time. I want to remind you to look at those other sources that I was talking about again, the Georgia Public Broadcasting physics in motion stuff, in this case, the electrical stuff, the segment that has to do with electric potential. You have to watch it because the study guide question has to do with what's presented at the end or in the middle of that segment. So make sure to watch that, but also read the textbook to understand these concepts. And there are example problems in the textbook as well, which I want you to be able to try to do. All right, so understand these things. That's all part of this learning process. Thank you so much. I appreciate it. And I hope that I will see you with good cheer and good health in the next lecture. Okay, thank you again. I really appreciate it. Talk to you later. Bye.